16.3, buffer effectiveness. And so we're going to discuss buffer range and buffer capacity. One of the things that influences how effective a buffer is would be the relative amounts of acid and base. That's one factor. So a buffer is most effective when the concentration of acid and the conjugate base are equal or very close to equal. That's when it'll be the most effective. So let's look at a specific example. We're going to compare two 1-liter solutions of a generic buffer. It's got a pKa of 5, and we're going to calculate the percent change in pH when 0.010 moles of sodium hydroxide is added to each. The more effective buffer will have a smaller pH change. The less effective will have a greater pH change. Just rip it open and crunch away. It's fine. So here are the two solutions. Solution 1 is 0.1 mole of the acid and 0.1 mole of the conjugate base, equal amounts. Solution 2 is 0.18 moles of the acid and 0.02 moles of the conjugate base. So if you add those together, they both contain 0.2 moles of something, right? The total number of moles is the same, but they're divided up differently. 0.18 plus 0.02 is 0.2. 0.1 plus 0.1 is 0.2. Yeah, that's okay. I did a double take on that when I was making the slide. So let's look at what happens here. Remember what we're doing. When we're looking at how the pH changes when you add something, an acid or a base, to a buffer. And you do two different calculations. One is the stoichiometry, and the other is the equilibrium calculation. So before the addition, we basically have no hydroxide, 0.1 molar of the acid, 0.1 molar of the conjugate base. And then we're going to add 0.01 moles of sodium hydroxide. This is a 1-liter solution, and we're doing this in moles. So after the addition, what we assume is that this strong base is going to completely react, and the hydroxide will go back to 0. And so this acid concentration is going to decrease by 0.01, or the number of moles, to 0.09. And the conjugate base will increase by 0.01. Okay? So we're just saying it's going to all react, and then we're going to calculate backwards to see what the hydroxide ion concentration is, because we know it doesn't go all the way over. And this is kind of what that sneaky problem on the exam was like in disguise. Okay, let's find a decent color here. So, can we assume that X is small? Or do we want to do the whole equilibrium calculation? We can use Henderson-Hasselbalch equation, or we could do the equilibrium. You know, our brains are all fuzzy from taking an exam, aren't they? We probably right now feel more comfortable doing an equilibrium concentration calculation, right? Because we just spent 2 hours doing those. Okay, so we'll just do that. So here we'll look at the initial. This is going to be just these numbers that we just figured out. And then we'll look at the change. So the change is we're going to say, well, it's going to go back this way a little bit. So this is going to be minus X, and this is going to be plus X, and that's going to be plus X. And so at equilibrium, this is X. This is 0.090 plus X. And this is 0.110 minus X. The pKa for this buffer, the pKa was 5. And notice when we have equal amounts of the acid and its conjugate base, the pH is equal to the pKa. Well, so that's the pKa, but to do this calculation, we need the Ka, right? Well, this one is, we get the Ka is equal to 10 to the negative pKa. So that's pretty easy. That just ends up being 10 to the minus 5. So 10 to the minus 5 equals the 0.110 minus x divided by x times 0.090 plus x. And then you can look at that and say, well, let's just do the solver thing because we're tired of thinking too much and we'd rather just do something. So 1 EE minus 5, I'm actually, I've decided I really like this TI-30X Pro calculator. I like it so much I ordered one for myself because this one is not mine. So I'm plugging all of this in, divided by x times 0.09 plus x. And I accidentally hit the clear button. That was just fabulous. There's really no recovering from that. I'm going to pause while I do this. Okay, so the first time I ran it, it wasn't happy starting with x is 0. So I started with x equals 0.2, and then it was okay. So it's telling me that x equals 0.1, basically 10999. I'm not sure I'm happy with that. Okay, so let's just erase this. So we started out doing it the hard way, and it wasn't going well. So I looked at the answer, and because I looked at this on Monday, and apparently I've forgotten some things since Monday. Today's Wednesday, right? I've had a hard time keeping track of the days of the week. Anyway, let's use the Henderson-Hasselbalch equation for this, and that says that the pH of this solution, this buffer solution, will be the pKa plus the base 10 log of the base concentration divided by the acid concentration. Oh, yeah, now we remember that. So this is 5.00 plus the log of the base is 0.100 divided by the acid is 0.09, and that's just so much easier. 5 plus log of 0.110 divided by 0.09. Yeah, there's a 0 in there. Sorry. Then we get 5.09. Went up a little bit.
That's supposed to say pKa or pH?
The pH will equal the pKa plus the log of this ratio.
Okay.
We kind of derived that.
Because it says initial pH is 5.
The initial pH is 5 because the moles of HA and the moles of acid and base were equal, and so 1 over 1. I mean, this is 1. The log of 1 is 0, and so the pH equals the pKa. Okay. Where I really got it from was right here, pKa of 5. Okay, so what is the percent change? It would be the difference between 5.09. So the percent change is going to be 5.09 minus 5 divided by 5 times 100. So that's going to be 0.09 divided by 5 times 100. 1.8%. Small change. Cheetos make a mess of your fingers, don't they?
Yeah.
It's convenient having a sink, though, in the classroom. You can wash your hands. They actually banned Cheetos at my kids' school.
Because of that?
Because, yeah, I mean, it's orange everywhere. And kids are sticky already. They sweat sweetness, and it just, they're always sticky. That's why my iPad looks like this.
You can make those without getting the powder on you and make it taste exactly the same?
Well, the natural Cheetos that don't have the coloring in them are better.
And they don't do that.
But, I mean, you just get a lighter orange stuff on your fingers.
They can do it without.
Can they do it? They really should.
Just do that. I know it is. They say it's part of the experience.
The experience, yes. Well, just like, lemon bars. Part of the experience is you forget and you inhale right as you're putting it in your mouth, and then the back of your throat and your lungs are coated with powdered sugar, and you spend the next 5 minutes coughing, right? That's part of the experience of eating lemon bars. It's a rite of passage. That and feeding Pop Rocks to the neighbor's dog. Okay, enough of a tangent. Let's look at the other solution. So this initial pH would be calculated just like this, okay? The pKa is the same. This is the same generic buffer. The concentrations are just different. The pKa will still be 5, but the pH isn't 5 because these concentrations are not equal. Okay? I can prove it to you, but you believe me? You don't want to see another calculation, so you're just going to believe me. Okay, so...
Blind trust.
Blind trust, yeah. Well, it'll get you all kinds of places. So here's before the addition, here's the addition. We're adding the same amount of sodium hydroxide. And then after the addition, we're assuming that this reacts completely. And so this is 0.17 now, because 0.01 of it reacted. And this is now 0.03. And so we can use the Henderson-Hasselbalch equation again. There goes the train. The pKa is still 5 plus the log. I had to use my videos from last semester at my class in Tulare, and they're like, why is there always a train going through the classroom? Yeah. Okay, the base, 0.030, divided by the acid. So 5 plus base 10 log of 0.03 divided by 0.17. And now we're getting the pH is equal to 4.25. So again, we can calculate the percent change. 4.25 minus 4.05 divided by 4.05 times 100. So that's 0.2 divided by 4.05. The initial pH is different. So here the percent change is 4.9%. That's larger. The initial pH of this one is 4.05. The initial pH of this is 5.
So when you're calculating the one right, shouldn't it be?
This is not the initial pH. This is the pKa.
The pH is 405.
The initial pH is 4.05, but the Henderson-Hasselbalch equation uses pKa, not the initial pH.
Oh, okay.
They happen to be the same here because we have equal amounts of acid and conjugate base. Any other questions?
If we're just to believe you that pKa, the solution 2 is the same.
I'll show you. So for solution 2, to calculate the initial pH, we would use the same equation plus the log of. Now the base is 0.02 and the acid is 0.18. This is what happens when you have popcorn for dinner. is really nice at the time, but then later, just wow. 5 plus base 10 log 0.02 divided by 0.18, 4.05.
And the pKa is given regardless. They gave it to you on the page before.
It was given on the page before. This is just, we're making up a problem here, a generic buffer. We're just saying, let's say the pKa is 5, but let's look at what happens when we use different amounts of acid and base. Here they're equal, here they are most definitely not equal. And that the fact that it's not equal means that adding the same amount of base, we get a much larger percent change in the pH. So buffer 2 is not as effective as buffer 1. The effectiveness it depends partly on the relative amounts of acid and base. You get your best buffering capacity or effectiveness when you have equal amounts. Any questions? So, to be reasonably effective, the relative concentrations of acid and conjugate base should not differ by more than a factor of 10. Well, what does that mean? Well, let's go back and look at this one. No, that's not what I meant to do. This one. 0.18 and 0.02. Do those differ by more than a factor of 10? Well, 0.18 divided by 10 is 0.018. So it is within there, but just barely. I think an easier way to look at it is to say, well, the ratio of base to acid should be less than 10, but greater than 0.1. The closer it is to 1, the better your buffer. But if it's within that range, it's okay. And so on the previous, that solution 2, the base was 0.02 and the acid was 0.18. 0.02 divided by 0.18. And that gives us, that's equal to 0.111, repeating. A little bigger than 0.1, not much. Okay, so that's just a kind of a guideline. That was relative amounts. The absolute concentration is also important. A buffer will be most effective when the concentrations of the acid and the conjugate base are high. The higher they are, the more effective it is. So if we look at that same generic buffer, but now we're going to have solution have concentrations that are 10 times higher than solution 2. And we're going to look at the same amount of sodium hydroxide being added. So this is the same imaginary buffer. So here we have 0.5 moles of acid and 0.5 moles of conjugate base. It's equal. And here we also have equal amounts, 0.05 and 0.05. But these concentrations are 10 times larger. And so we'll calculate again. So this table is showing us the stoichiometry part of the calculation, and then we'll just forget to select the pen and then accidentally change the slide instead, because that's how the day is going. pH, the pKa is still the same, 0.05, plus the log of the base over the acid, so 0.51 over 0.49, 5 plus base 10 log of 0.51 divided by 0.49, 5.02. And so the percent change is going to be 0.02 divided by 5 times 100. I'm not going to write all that out, 0.4%. And then over here, smaller amounts, lower concentrations of the conjugate acid and base. Relative amounts are equal, but again, adding in this 0.01 moles of sodium hydroxide and
That's not right.
That's not right.
That should say.
Okay, so I fixed my slide, but I lost my mind. Pretty much just is gone. Is it time for spring break yet? This came out to be 5.02, and the percent difference was 0.4%. Ooh, I remembered that. That's amazing. Okay, now we can look over here and see correct numbers. So, Henderson Hasselbalch again, pH 5.00, that's the pKa, plus the log of the 0.06, don't rotate on me, please, 6 divided by 0.04. You don't like my tiny zero? It's just checking to see if you're awake. 0.06 divided by 0.04. So now the pH is 5.18. Percent difference then will be 0.18 over 5 times 100, which is bigger. 3.6%. Yeah, so the percent difference is 9 times bigger because the concentrations were 10 times smaller. Now, is there a relationship in there? I don't know. I don't care.
A little bit.
The idea is higher concentrations of your buffer components gives you a more effective buffer. Let's make sure I didn't skip something by accident.
Is that because there's just more of it to buffer?
Because there's more of it. Yep. And so when you add the same amount of acid or base, it changes those concentrations less relatively. And so the ratio is closer, and so the pH doesn't change as much. Did you have a question?
Yeah, you said that the buffer components give what? The higher concentration?
Higher concentration of buffer components, and by buffer component, I mean the weak acid and its conjugate base, or if you have the other kind of buffer, the weak base and its conjugate acid. It's more, the buffer is more effective at resisting pH change if those concentrations are higher. Then there's also a matter of the effective pH range of the buffer. And that's going to be, the absolute range will be centered around the pKa of the buffer itself. But what's the range over which it's going to be effective? Well, remember we said that we had that guideline ratio of base to acid should be greater than 0.1 and less than 1. I'm sorry, less than 10. Yeah. So our lowest pH would be where the base is equal to 0.1 times the acid. And I guess I can't remember what I was going to write in these blanks. I think maybe I was going to calculate the pH range for our imaginary buffer from the previous few slides. So in this case, my voice is going too. Yeah, I'm just going to use the pKa thing. I'm just going to use the 5.0. So let's look at that same 5.0 made up buffer. So now the base, what this gives us is that the base over the acid is 0.1, right? So then here we're going to have the log of 0.1. The log of 0.1 is -1, right? And so this ends up being a pH of 4. The highest range in which this imaginary buffer with a pKa of 5 is going to be effective will be that 5.0 And here we're going to have the log of 10. What's the base 10 log of 10? 1, but it's plus 1. And so here it's 6. Isn't that cool? I picked this 0.1, or, well, Mr. Tro, Dr. Tro picked it. I didn't pick it. This is straight out of the book. The 0.1 and the 10 come from that guideline for where the buffer is effective. If you get below a pH of 4 for this particular buffer, your ratio is going to be off and it's not going to work as well. The pH will begin to change more and more. So, here's a nice rule of thumb as well. The effective range for a buffering system is 1 pH unit on either side of the pKa. So, buffers are something that biologists use, right? Buffers are things that get used in the healthcare industry. And how do you choose what to use for your buffer? Well, one of the things is, what kind of a pH are you trying to buffer? Do you want the pH to be around 5? Do you want it to be around 8? You're going to choose your buffer remembering that it's going to be most effective when the pH is close to the pKa. And then you can adjust the pH, the actual pH of the buffer, a little bit either way within that plus or minus 1 pH unit, just by adjusting the ratio of the base to acid. So we're going to do an example here. Which acid would you combine with its sodium salt to make a solution buffered at pH 7.35? So here's 4 acids to choose from.
7.54, maybe?
Maybe this is the only logical choice, right? We're going to look at whatever acids, weak acids we have available, and we're going to choose one whose pKa is close to the pH that we want the buffer to be. So we're going to choose the hypochlorous acid. I'm going to choose that guy. Now, if we have 500 milliliters of a 0.1 molar solution of the acid, what mass of the sodium salt would we have to add to make it into a buffer? Oh. We have molarity, and we need, right? Okay, well, let's think about this. So we want the pH, let's use Henderson-Hasselbalch, okay? So we want the pH to be 7.35. That equals the pKa, which is 7.54, plus the log of the ratio of the concentration of the base to the concentration of the acid. Right? So if we have, and remember, we can do this either in molarity or we can do it in moles, because the volumes are the same and they cancel out. Well, here we have half a liter of 0.1 molar of the acid, right? So 0.5 liters times 0.1 moles per liter is going to be what? Be 0.05. And there really should be 2 sig figs in there. Moles of the acid. Everybody cool with that? So this is the number that I want to stick in here, and then I'm going to solve for moles of base. So the moles of base, I need to find out how many grams of the sodium hypochlorite I would have to add. Okay, so I'm just going to do it this way. I'm just going to erase. Come on, erase. I'm going to take that out and put in the .050 moles. And now we're going to solve for the base. Well, we're going to take the 7.54 and subtract it from this side. So we're going to get a negative number over there, but that's okay. 7.35 minus 7.54. So we're going to get negative 0.19 is equal to the log of the base over 0.050. How do we get rid of the log? 10 to the x of both sides. So 10 to the minus 0.19 is going to equal the moles of base divided by 0.05. So moles of base is going to be 0.05 times 10 to the minus 0.19. Sounds really weird, doesn't it? We end up with 0.03228 moles. How do we find the mass of the corresponding sodium salt? It's not per liter because I used moles here. I was actually thinking ahead. You could plug the 0.1 moles per liter in, then you'd get the concentration, and you'd have to convert it to moles. But I kind of did that ahead of time. I'm not going to completely finish this one out. So the sodium salt would be NaClO, and you'd have to find the molar mass, and then you take that and you'd multiply grams per mole, and you get the mass that way. And that's a very practical problem. It's like, okay, I need to make a buffer. It needs to be this pH. This is what I've got. What do I need to add into it to make it into a buffer? Any questions? So, like, there's this huge array of questions that could be asked about something like that, right? So fun. Buffer capacity. So we talked about buffer effectiveness and buffer range. Now we're going to talk about buffer capacity. That's the amount of acid or base that you can dump in there without causing huge changes in the pH. The capacity is going to increase with increasing absolution. No. Okay, stop. Okay, I fixed my typo. So the buffer capacity will increase with the increasing absolute concentrations of the buffer components. It also increases as the relative concentrations of those components become more similar to each other. So if the components are roughly equal, your capacity is greater. What happens then is as you're adding, say, sodium hydroxide to your buffer, the concentrations of the weak acid and the conjugate base are becoming less and less similar, and eventually gets to a point where you overwhelm the buffer. Now, some buffers are designed to primarily neutralize added acid or primarily neutralize added base. And so those might be overweighted in one of the buffer components. If you know that the biggest challenge to your buffer is going to be acid, then you're going to want your base concentration to start out higher than your acid concentration, maybe even close to almost 10 times higher. Whereas if you're going to have to neutralize a lot of base, you'd want it the other way around.